Hello, everyone. Welcome to 1.5 Degrees, the podcast where together we explore the science, solutions, and stories involved in the fight against climate change. I'm your host, Heidi Pan, speaking with the professionals behind the latest research, policies, culture, and innovations shaping our response to global environmental challenges. For today's episode, I'm joined by Dr. Amit Lath, who is a professor teaching at Rutgers University, to discuss his work, the physics of the greenhouse gas effect, and more. Professor Lath has been teaching and conducting research since 2001. A particle physicist, he has worked at major particle accelerators and helped discover the Higgs boson in 2012. He earned his undergrad and PhD degrees from MIT, where he studied under Nobel Prize-winning physicist Henry W. Kendall, a pioneer in the discovery of quarks and founder of the Union of Concerned Scientists. Thank you so much for joining us today. It's such an honor.
Thank you. Thank you for having me.
Can you talk more about what it is that you do?
Okay. So simply put, what I do is trying to understand nature at the smallest scales. So this is referred to as subatomic physics or particle physics. It can also be referred to as high energy physics, because the rules of quantum mechanics say that the smaller the thing you want to measure, the smaller the scales you want to see, the higher energies are required. So the Large Hadron Collider, where I work, is 17 miles around. It's a circular ring 17 miles around. It's the largest experimental thing ever built by humans. And one way to think of it is it's the strongest microscope ever built. We're trying to look at, the substructure of nature.
What first drew you to particle physics, and how did you decide to pursue a career in?
I grew up in the 70s and 80s. There was a TV show at the time called Cosmos with Carl Sagan. And even before the TV show, I was very interested in astronomy and astrophysics. I'd read books on black holes. I was that kid in class. And then I got to college and I took some courses in astronomy. And there's a lot of memorization of, how far things are from each other and how big. Junior year, most physics majors take a course called Junior Lab. It's atomic physics. I had Professor Kendall as my undergrad lab advisor. And, we just started chatting, things weren't working because, they were ancient, like Manhattan Project cast-off devices we were using in that lab. And, we would have to fix it. And he just said, hey, do you want to come work for me in my lab? He was doing some side thing. And I said, yeah, sure. I'm looking for a research position. So, and then I guess I didn't leave until I finished my PhD, and I stayed with him through, I did my undergrad project. And he said, why don't you just stay for your grad school? I said, I'd gotten into a couple other grad schools, but I stayed with him and then got my PhD around 94.
That's so cool. So it's kind of like happenstance. As a part of your work, you're part of the team that discovered the Higgs boson, which is super cool. Can you describe what that moment was?
It was really exciting, but not in a, aha, eureka way. So before the LHC was built, so let me just put in some context. Before the LHC was built, there were already, there were precision measurements at the W, the Z and the W boson. And in fact, my PhD thesis was one of these precision measurements that narrowed down sort of the window where the Higgs could be. So we knew the Higgs was sort of above a certain level and below. And so we knew it had to be in this area. And then, when the LHC was built and started taking data, we sort of knew what we had to do to get it. And there were different groups doing different, ways, different channels, it's called. And the Rutgers group was part of this, what's called a diphoton. So the Higgs goes to 2 gamma rays. The way these experiments are done, they're done blind. So you don't look at the data, it's like drug tests at the pharmaceutical.
Yeah.
You don't actually want to, bias or something. So it's called blind analysis, okay? And so there is a point where you're like, okay, we're done. We've done the best thing we can. All the analysis strategies are frozen. We're not going to touch them. Let's look at the data. So that's called the unblinding. And boom, there it was at 125 GeV, a little excess. It was statistically significant. And, so that was a big video conference because everybody was connected up. And then, we're like, and then of course, what you do is you try really, really hard for about a week to get rid of it.
Hmm.
right? I mean, you really, 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 I mean, your job is at that point to figure out everything that it could be, where the standard, what's called the standard model, standard physics, plain vanilla physics could be faking this, right?
Hmm.
So, yeah, so we were really deeply involved in that, and we couldn't make it go away. And then we published. Yeah, so
Yeah.
that's how it actually sort of, that's how most discoveries, are done, is that, you find something and then you try very, very hard
Right.
and to make it go away, to come up with a narrative where it's just a fluctuation. And
Hmm.
sometimes you do make it go away. There was
Hmm.
this result a while ago where they thought neutrinos were going faster than light. The faster than light neutrino, you can Google it. And
Okay.
that to be, for about a week or so, they're like, oh my God, neutrinos go faster than light. No, turned out to be a glitch in the cabling. They found it.
Being able to work at these major particle accelerators, including the Large Hadron Collider, like how has it shaped your perspective on the universe?
Oh yeah. So yeah, I think if you work in science, I mean, it doesn't matter what science, you can be working in biology,
Hmm.
it makes you quite humble because, I mean, you realize what a small part of the universe your daily life, your concerns really are.
Hmm.
I know people say that, astronomers always say that, right? They're like, oh, you look at the galaxies and the whole, super clusters of galaxies and you feel
Right.
very small. But the same is true when you're looking at the subatomic world. Okay, you look at the subatomic world and you realize that all the rules of nature that you thought were, solid things, like, I can hit the table and my hand doesn't go through the table, and, cause and effect and just, normal things that you just take for granted, just living at, macroscopic scale, living at it.
Hmm.
These are just ephemeral things. These are just emergent concepts that survive from the subatomic world. My colleague, a theorist here, Scott Thomas, has this statement that objective reality is an emergent concept. The rules in the subatomic world are very, very, very much probabilistic. Okay, they're not, cut and dry as they are in the macroscopic world, and we don't actually quite understand fully. Right? We're still figuring it out. But that just, that has to affect your thinking. That,
Mm.
everything you think is real because you're dealing with large numbers of particles and it's not true if you delve down. It's a
Mm.
very, very different world at the subatomic level. It has to affect your thinking.
Definitely something to think about for listeners. But yeah, I guess so talking about your PhD advisor, Henry Kendall, who is a Nobel laureate, how did his work influence your own scientific career?
So, while I was both an undergrad and a graduate student, I would see him, participate both in the scientific arena and, he would go on talk shows like, Donahue, he got interviewed
Hmm.
by PBS, and one thing that Henry always had, he had credibility in both the scientific and, environmental arenas because he took extreme care to stay within the boundaries of what was unimpeachably true.
Mm.
Okay. He never exaggerated for effect. And I think a lot of people, in the environmental community, especially the ones who are not scientists, are prone to that. They'll
Hmm.
say things that, aren't, the Antarctic ice sheet is going. No, I mean, there are probabilities, but, you really have to know what's unimpeachably true, what's absolutely true, and what's conjecture. And so he knew that, and he would stay within, and even when something would help his narrative, he did not fall into that,
Hmm.
and he always knew, like, if you ask him something, what's the probability, what's the chance that the Greenland ice sheet is going to fall into the ocean, okay, it's probably 10%. It's
Hmm.
not necessarily going to happen. And he knew not only the uncertainties, he knew how they were derived. And, not saying something without understanding where that comes from and, knowing the quantitative. And I think a lot of people who are environmentalists, they don't realize you have to be quantitative. You need numbers. You need to be, people say, oh, I'm not good at numbers. You need to be good at numbers. Right?
Convex.
You'd have no
Convex.
credibility without that.
And is that 10% figure like accurate, or is that just a number you came up with?
I don't know what the latest IPCC projections are. Things change.
Right.
The IPCC has been putting out, I'm sure your listeners know about the IPCC reports. They've been putting out, reports, and they actually have consequence of the global warming, and every little thing that could happen, they have a likely, less likely, more likely, and that changes depending on, the computer models and observations. So I don't know what the latest numbers are, but that's roughly right. I could look it up. I could look up the latest. I think the latest IPCC report is from 2022. But there is definitely a non-zero chance there could be catastrophic ice loss. Yeah. But it's not,
Yeah.
it's not imminent tomorrow. That's
right. Although I think this year it was kind of like, I don't know. Yeah. I guess like we're kind of transitioning into then like talk about environmental and climate science. What is the connection between particle physics and climate science?
Okay, so yeah, I saw that question. That's an interesting question. One of the things that I would say is a deep connection is that both are very complicated systems. Okay, so you can't just do it by thinking, writing down on a piece of paper. It's not a simple correlation. It's the Earth climate is a complex system. Subatomic particle physics is a complex system, so you depend on very detailed computer simulations. Because too many things are interacting with too many other things, right? So we're very used to in particle physics, like when we did the Higgs discovery, we had all of the standard physics, the plain vanilla physics that we knew about simulated, and within, and we would tweak it a little bit within uncertainties and simulate it again. So we had a whole raft of simulations that when we saw the Higgs, we were like, okay, this is not some glitch.
Right.
This is a real thing. Same thing with climate science is that we have. So if you look at the IPCC reports, they have computer simulations. It's very, some of the biggest computers in the world, are dedicated to climate simulations. And not only that, the climate simulations have gotten much, much, much better since, I was a student. I mean, back in the day, we had, in the 80s, they could simulate the atmosphere and land, but they didn't have, the ocean and air. And, they started putting in aerosols and sulfates and vegetation, atmospheric chemistry. Even today, one of the problems is clouds. We don't really have good cloud simulations with the cloud. The pixel size, although it's gotten small, as computers have gotten bigger, they're still hundreds of kilometers, and clouds are, 1 kilometer. So you can't really do clouds very well. But given all of that, if you look at the climate projections and with and without human greenhouse gas emissions, it matches where humans started emitting in 1850, the Industrial Revolution. It matches really, really well. And it does not at all match no human activity. So, and it's in the IPCC report. And it's, to me, that's, it's very statistically significant. I think at this point, you could argue that it doesn't have, the greenhouse gases emitted by human activity are not having an effect. Now, people, will argue, people who are not used to being convinced by, complicated computer models will argue. But, as a particle physicist, I'm used to taking, computer models seriously.
And if you that like graphic that you wanted to share, I think you can share it now, but also you could just like email it to me and I could just edit it in.
Okay. Can you see it?
Yes, I can.
Okay. So what we're seeing, this is from the IPCC 2021 report. And the first thing I wanted to show you is, so this is global surface temperature changed since 1850. So 0 is 1850. And you can see that starts at 0. And the black line is the observations. And you can see it's gone up by, so it ends at 2020, but it's, the title of your podcast is 1.5.
Mhm.
right? So we're almost already there. Yeah, what you can see is they do a bunch of different simulations.
Mhm.
And the green, I want you to look at the green band, if you can see that, called natural causes. And without any human activity, of course, there wouldn't have been any change in temperature.
Mhm.
The pink one is just greenhouse gases. And if there were just greenhouse gases, we would have reached much above 1.5 by now.
Mhm.
But the simulations also take into account aerosols, so things like sulfur dioxides and particulate matter
Mhm.
that we emit, and that actually reflects sunlight.
Mhm.
So, and that has a negative, it has a cooling effect. So when you add them all in, now notice, so that's the gray one combined, human and natural causes, including greenhouse effects and aerosols. That matches, the gray matches the observations really,
Mhm.
really well. The other thing I want you to take away from this, and if you were in 1990, so go on the x-axis, find 1990, right?
Mhm.
Now, the difference between the green band and the black isn't that significant in 1990, right?
Mhm.
So if you were a scientist in 1990, you would say things like, if you look at the IPCC reports, they're very cagey. They say things like, global warming is possible. They say things like, it may be happening.
Mhm.
There are indications, but they don't say, but now, in 2021, 2022, they're like, there's no doubt it's happening.
Right.
So if you look at the IPCC reports through the years, they very, very carefully, very, very slowly become more and more confident. And that's what
Mhm.
scientists do, right? Unfortunately, people who want to debunk quote unquote global warming, they'll go back to these old
Yeah.
reports and say, oh, look at that. All these scientists can't even agree if global warming. Well, because it takes time,
Mhm.
so this is what, proper computer simulations do. And then there's a band in the gray, right? You don't just run one simulation, you run all your uncertainties. If you don't understand clouds, you run it with lots of clouds or no clouds. If you don't
Mhm.
understand the Earth, the ocean atmosphere interface, you run it with high connected, ocean air interface and low, etc. The vegetation, dynamic vegetation, you change it up and down. And that's where you get that gray band. And look at the observations, they're right smack in the middle. I don't think you can argue with this thing.
Mhm. Yeah, I was gonna ask what the bands were, like why they were like not just one line, but yeah, that's so interesting. Thank you for sharing
Yeah.
that.
So this is part of the IPCC report. They put out stuff like this all the time, and I think
Mhm.
viewers can find it. I mean, they should just go. I mean, it's a very dry report because it's written by hundreds of
Right.
like me, smarter people than me. But yeah, it's not meant for easy reading. But the pictures,
Mhm.
there is an executive summary for political decision makers, which
Mhm.
has things like this with good.
I guess like kind of going into more of the physics. So what fundamental physics concepts are more important, or I guess most important to understanding global warming?
So yeah, so when I teach my global warming class, I'm trying to reach people who are not STEM, so they're not necessarily, conversant with physics concept. So I
Mhm.
tell them the two things you really need to know, and these are concepts that sophomores, undergraduates learn if
Mhm.
they're physics majors. And the first one is black body radiation.
Mhm.
And that one, everybody's seen. You take a piece of iron, you put it in a fireplace, and it starts to glow red. And if you put it in a furnace, it'll start to glow white. So the hotter a thing is, the shorter the wavelength. You start from red to whitish, and then bluish. So the color, the black body radiation is emitted, and it's the wavelength it emits proportional to the temperature. And you can see it. I mean, we're human beings, and if you've ever had infrared goggles, you can see that human beings, because our bodies are at 98.6 degrees Fahrenheit, we emit in the infrared. The Earth itself has a surface temperature of 65 degrees Fahrenheit. So it also emits infrared, but at longer wavelengths. The sun is also a black body, radiates black bodies but it's at 10,000 degrees Fahrenheit. So it
Mhm.
emits in the visible with much shorter wavelengths than the human body or the Earth. So visible and ultraviolet. If you look at Sirius, the dog star, it's much, much, much hotter than the sun. And looks, if you look up there, it looks bluish. Our sun is, more yellowish, but Sirius is bluish because it's much hotter than the sun. So things radiate light depending on their temperature. The other thing is the amount of light you radiate depends on temperature to the fourth power. Those are two things about black body radiation. And the other thing you need to know is greenhouse gases like carbon dioxide, they resonate. So you can think of carbon dioxide as a little springy molecule. So you've got carbon and two oxygens, and they can vibrate. It can vibrate, it can have different vibrational modes, and that vibrational mode is in the infrared. So if you have a tuning fork, it radiates sound at a very specific frequency. It can also absorb sound at that frequency and start vibrating and re-radiate it. Carbon dioxide is exactly the same way, but with a specific frequency of infrared. Unfortunately for us, or fortunately for us, is that happens to be at the same range that the Earth is radiating. So the Earth gives out infrared because it's a black body at 65. Carbon dioxide is there going, oh, I like this one. I'm going to start vibrating. And then it re-radiates. It goes back down and it radiates, but now it's radiating, isotropical all over the place. So the radiation that would have gone into space directly, now some of it comes back down. So now the Earth says, oh, not all my black body radiation is making it into space. I better turn up my temperature so I radiate more power. And then eventually the temperature of the Earth is at a point where all the power that's coming in from the sun gets radiated back into the space. Because, the Earth cannot hold on to energy. Everything that comes in eventually has to get back out into space. But the Earth maintains, it has control over the thermostat. So the Earth basically turns up the temperature until the input equals the output.
And can you go into how the interaction of infrared radiation contributes to global warming?
Yeah, so infrared radiation is something the Earth emits because everything emits some form of radiation. If you have a greenhouse gas like carbon dioxide, it will prevent, it's like having a blanket, it'll prevent some of that radiation reaching out into space. But then the amount of radiation depends on temperature to the fourth power. So whatever body is doing the radiating has to increase its temperature so that the amount of radiation coming in. So there's 240 watts per square meter hitting the Earth. Well, 240 watts per square meter has to leave the Earth. That has to balance. So if you have greenhouse gases trapping some of that, making it inefficient for you, basically spend all the energy that you're getting, you'll have to increase your temperature. It's a straightforward thing.
And what are some misconceptions about the greenhouse gas effect that you commonly hear or might address in your course?
Yeah, so one of the main things that, if you talk to people about global warming is they conflate climate and weather. So climate is something that, it's basically a long-term thing. It's an average over the entire Earth, right? And we have a pretty good understanding of climate. Now, weather, we don't know more. I mean, if you were to say, okay, what's is it going to rain on my graduation day? I know I can't tell you, because if you can't even say if it's going to graduate, if it's going to rain on a given day in June, how can I trust you about anything? But you can. I mean, climate is an average over, so, it's not true that global warming means that all places will warm up by 1.5 degrees uniformly. Some places will actually get colder. Europe, for instance, the meridional current, the Atlantic meridional current, if that dies out because of fresh water coming in from the Arctic, Europe could actually get significantly colder because it's unreasonably warm because of ocean currents. You stop the ocean currents, Europe actually starts to look like northern Canada. So people don't really understand that, it's cold in January. How can there be global warming? Right? A senator who actually, it snowed in Washington, D.C., he brought a snowball into the Senate chambers.
Oh, Jesus.
And that's just ridiculous, okay? I mean, we can predict a few things. I mean, we have climate model. One of the things that is going to happen is there's going to be more, as things warm, but, we're a planet basically covered in water.
Hmm.
As things get warmer, there's going to be more humidity. The air is just going to contain more water. That makes air heavier, right? A tropical storm that would have just been a tropical storm might become a hurricane. Type 2 hurricane might become a type 3 or 4 hurricane. So those kind of things, but these are probabilistic things, right? You can't say, oh, that particular hurricane became a hurricane due to global warming. So
Hmm.
people aren't very good with probability. So that's
Hmm.
one of the problems.
So we were on the subject of Earth's water. So you wanted to mention something about Mars, Earth, and Venus.
Yeah.
They receive
So
similar amounts of sunlight. Yeah, why are their climates
yeah,
so
Mars,
different?
Earth, and Venus are roughly, not exactly, but they're roughly the same distance
Hmm.
from the sun. They don't get exactly the same amount, but if you look at the amount of power, this energy they get per square meter, Mars is like a few hundred, we're at about 200, just roughly the same amount, you know, within a factor of two. But then you say, well, look at the actual surface temperatures. Mars is basically frozen. And that's because it has no greenhouse. So Mars is basically, so it's actually an exercise we do with our students. You calculate the temperature of all of these planets without any greenhouse effect. And Mars it's called the bare rock temperature of a planet,
Hmm.
right? So the actual surface temperature of Mars is basically equal to the bare rock temperature of Mars because it has no trapping, no greenhouse. The bare
Hmm.
rock temperature of Earth is like -1 degree Fahrenheit. Okay, now the actual
Hmm.
surface temperature of the Earth is much higher than that because we do have some greenhouse effect. Venus, the bare rock temperatures are also very, very cold, but Venus is about 800 degrees Fahrenheit because it has what's called a runaway greenhouse. It just
Hmm.
has a lot of greenhouse. So you see, it's basically, I mean, it's almost like somebody arranged, it's like a Goldilocks thing,
Yes.
Earth is just warm enough to have liquid water on the surface. Mars has no greenhouse, so it's at, basically black body radiation has nothing to impede it, so it just
Hmm.
radiates everything out. Whatever sunlight it gets goes out, and uh, Venus is just ridiculous. It's the surface has to turn its temperature way high to punch through all the greenhouse effects it has.
So, I mean, in the coming years, probably gonna be attempts at this. Could a human-engineered greenhouse gas effect make the planet Mars more habitable given its thin atmosphere?
Well, first of all, there isn't much of an atmosphere on
Hmm.
Mars, right? I mean, there is some, of course, you can fly a helicopter on Mars, so there is some air, but there's not a lot of carbon dioxide at all. I mean,
Right.
there's not a lot. I guess, so you'd have to get on the surface of Mars. You'd have to run some chemical reactions, and I am not a chemist, but I'm sure that, you could with enough resources and right people could do. I mean, you do that in high school chemistry, right, where
Right.
you have these crystals and then oxygen comes out, and I'm sure you could do that. I don't know whether it's worth it. I'd never want to say no because then people will say, aha, look, we found this trapped reservoir of CO2 under the Martian poles and we're going to release it, and
Oh, jeez.
then we found water, and we're going to do electrolysis and put oxygen in the Martian. Who knows what 100 years from now people will be.
Right.
I think, but the main thing is you need enough. Right now on Earth, we're about 400 parts per million.
Mhm.
You'd need much more than that because just total volume of the total number of molecules in the Martian atmosphere is just so small.
What lessons can we learn from planetary climate studies that could help address climate change on Earth?
Well, I think we've learned quite a lot already. I mean, we know it's happening. I think, certainly people of your generation are not in doubt that,
Hmm.
human activity is causing climate change. Unfortunately, I think the lessons, going forward, we need to learn are more about human nature and
Mm.
politics. And I think the trouble, is that people are like me, scientists in general. I mean, we make fun of people who are like, oh, I don't like numbers. And we are similar in that way, scientists and all, oh, we don't like politics. We don't like to get involved in
Mm.
politics. Oh,
Hmm.
sociology is just too difficult and complicated. And I think, unfortunately, we have to. Okay. And people have done some studies, and, it's not surprising that people don't want to address this. It's happened before. So there's a book by Jared Diamond. He's a professor at UCLA called Collapse. And one of the things, one of the incidents he talks about is the Greenland Norse. So there's Danish people, they go to Greenland because, there's a warming period in the Middle Ages. Yeah, it's nice and warm. And they're like, oh, yeah, we're going to bring our cattle and, we're going to do the farming thing and just, be, Nordic people, but in Greenland. Turns out, after a couple of hundred years, a few generations, it starts getting cold again because, hey, it's Greenland. And they have neighbors. They have people there. They can, the Inuit, they live in Greenland, but they don't live like farmers. They, they hunt, they fish, and they're nomads. They don't stick in one place, frozen tundra. So they could have done that. They could have said, okay, look, here's a picture of what we could, but they didn't, right? And the entire settlement just died out, It was horrible because of identity, right? It's like we have an identity as farmers, as Christians, as, we farm, we don't live like these savages. That's what they thought of the Inuit. They died rather than change their ways. And now, of course, in the 21st century, look at them and say, ha ha, you silly things, you could have survived. But, we have our identities, we have the way of living, and we're not willing to change them, right? I mean, how different are we from these guys, live a farming life in, Arctic tundra and died. I mean, we're not that different. I mean, human nature doesn't change, right? And most people will probably keep doing what they're doing until they can't. People still buy. I mean, people buy houses on the shore, on the barrier islands, until they can't get insurance. Things people don't change their ways. You can show them all the graphs you want. Scientists and all have to start learning more about human nature. We can't just show you graphs and say, change your ways. It's like, human beings don't work that way.
And I guess like kind of on that subject, besides just talking to each other, what do you think are some urgent steps that scientists and policymakers should take to mitigate climate change?
Okay, so this is we need to stop burning coal. Okay, okay. If you walk into your house and it's cold, you look around and you see the big French doors that look out into your deck are open, right? You don't go around saying, oh, I better put caulking around my windows or, no, you close the French doors. First thing you do, right? Burning coal is the open French door. Okay, we need to do that. Okay, so we need to be very careful because, there's all sorts of kinds. So people will say, oh, everybody should have electric vehicles. Well, electric vehicles are fine, but if you tell PG&E that your electricity demands are going to go up,
right?
If there was a coal-fired power plant, in Homer City, Pennsylvania, or in West Virginia somewhere, that they would have retired.
It's gonna
now they're like, oh, maybe we keep it running another 5 years.
Yeah.
And coal is horrible. Coal is twice as bad in terms of carbon dioxide produced per unit of energy compared to even natural gas. Natural gas is actually twice as good. So if you could just take all the coal-fired power plants and turn them into natural gas-fired power plants, you'd make this huge difference in carbon dioxide emission. And, people are instead going on about solar and wind, which are tiny, okay? They're not actually gonna, nuclear, we should really be building more nuclear power plants. I mean, I don't understand why we're not. And I don't understand the environmentalists who are anti-nuclear because, a nuclear-fired power plant, you give it nuclear fuel, it runs for like 3 years. Unlike, you get one of these panel trucks, that's all you need for several years, producing 5 gigawatts of power. So we should be building that. We should probably eliminating coal-fired power plants, and we're not. I mean, countries like China and India are actually building new coal-fired power plants. And once you build a new coal-fired power plants, it runs for 40 years. It's a 19th century fuel that we should not be burning in the 21st century. There's lots of things you can get involved in, including, plastic drinking straws and whatnot. And they're all, minor sprinkles on the cupcake compared to, okay, coal is the big thing we need to deal with. Once you do the numbers, it's so obvious.
Mhm.
That everything else that people worry about, plastics and recycling, it's meaningless. It's
Mhm.
meaningless at the face if we're still burning coal. Electric vehicles, I don't know. I mean, I'm ambivalent about electric vehicles because I think, on one side, okay, you stop burning octane, you stop burning hydrocarbons,
Right, but they're
and
still on the power grid
yeah,
that's powered by
and you
coal,
switch to
right?
coal.
Yeah, that's not much better.
I mean, in
Um,
terms of carbon dioxide emitted, if you take, it's roughly a 35 miles per gallon car. You're better off than buying an old Honda.
right. Yeah, okay. So before we kind of wrap up, I wanted to talk more about like your experience with teaching. How did you get into like being a professor?
Okay, so, once I got my PhD, I wanted to stay in research.
Hmm.
I like particle physics, so I looked around. So there's two options. You can go work in a national lab like Fermilab or Brookhaven National
Hmm.
Lab, Stanford Linear Accelerator, or you can, try for faculty positions, which are, they tend to be difficult.
Yes.
But Rutgers had an opening. This was, yeah, 20 years. One of the professors was retiring, and so I applied. And at the time, I had a couple of papers that I'd written as a postdoc. I was able to talk about, and then I'd never actually done any teaching when I got hired, so I had to
Hmm.
learn, how to talk, without jargon, understandable. And yeah, I'm still learning. I'm still learning how,
Hmm.
over the last 20 years, there's been a lot of research on how to teach properly, how to
Hmm.
reach students. Compared to how I was taught physics, we are so much different now. When I was taught physics, it was sort of like throw you at the deep end of the pool, and that's what's done to us at Moscow Tech. Well, that is how you will learn.
Hmm.
So, but we understand now how people learn physics. We're still doing studies. Physics education research and math education research
Hmm.
are, major fields of study now. It's interesting. I really like teaching. I mean, it keeps me, connected to young people, and so that's very important. I mean, if I'd gone
Hmm.
to a lab, I would still be doing research, but I wouldn't have access to, students and how they think. And it's important to me to teach things like this. Yeah.
Yeah, certainly. This is a classic kind of cliche question, but what is your like favorite or least favorite aspect of what you do today?
My favorite aspect, it's still, yeah, doing analysis on the data from the Large Hadron.
Hmm.
We're at the energy frontier. Nobody's ever looked at what we're looking at. And then when you make a discovery, like the Higgs discovery or other, smaller ones, it's just amazing. It's, nothing compares to that. You're looking at, nature at its most fundamental, at its smallest. And nature doesn't want to give up its secrets. You need to build 17-mile circumference, and you need 4,000 people to run it. It's difficult, but I think just and being in a building and being in a community with other people who think like this makes it worth it. And people who get excited by doing research and finding out things about nature, not just physics, chemistry, biology, whatever. I mean, I like to talk to people who are really, really interested in what they're doing. They wake up at 3 in the morning and jot things down. I love that.
That's so cool. And then your least favorite, if you have a least favorite.
The least favorite is I've taught classes where students were sort of forced to take physics. These tend to be in the medical field, pharmacy, things like that. And, for some reason, somebody decided that, the MCATs were going to have a physics component, so they have to take physics. And, I
Mhm.
try my best to make physics understandable and even exciting. They come in with an attitude that,
Mhm.
this is something I'm being forced to do. I don't like it. I don't like the instructors. And that has a dampening effect on, the entire situation.
Yeah.
And you come away from that just feeling down,
Mm.
and it's like, you have to sort of tell yourself, no, what I do is important and interesting. And if they're not interested in physics, why are they doing, why do they want to go into medicine? Is it just, I mean, I could come up with a bunch of other things, administrative things, applying for grants, but that actually, have to say, is having to deal with students who are just going through the motions, who are just uninterested in just academics in general, physics in particular. That really is difficult. And sometimes, you're like, okay, is it something I could do better? And I've come to the conclusion is no, because I've taught physics majors and engineers, and I'm able to reach them. People do get
Mhm.
excited when you start talking, and they come after class, and why can't I do this with this set of students?
A wrapping up question. If you could turn back time, butterfly effects aside, and tell your younger self something that you wish you'd known, I guess like that you've now learned from life so far, what would you say to them? Could be at any point in your life.
I don't know. I mean, it's if I don't really believe in time travel, so I think
Yeah. I don't think anybody should believe in
as
time
a
travel.
even as a fictional exercise, I tend not. I mean, it's like you might as well just have unicorns, I think I would just say, things they work out okay. I mean, I don't know whether me telling my younger self a thing will change things, in which case I would be wrong.
Yes.
Like maybe me telling you things are going to be okay. Tell them, maybe try Brooklyn Boys Pizza a little earlier than I did because it's really good. I don't know. I guess I could tell myself to invest in Google back when they actually offered scientists and engineers like a preliminary, you can go in and like buy a certain amount of stock. And I'm like, what
Interesting.
is this search engine? And same thing with Apple. I mean, when I was in college, there was an Apple versus PC fight,
Yes.
and everybody was like, oh, PC, IBM is going to win this because I know it doesn't really matter. Apple is this sort of fringe thing, and everybody's going to start using IBM PCs soon enough, and just let's not even bother with Macintosh. And yeah, that was wrong. Yeah, so maybe something like that. I don't know.
Who knows? Yeah. But yeah, no, thank you so much
But
again, Professor.
yeah,
And yeah, for listeners who might want to, keep up with the work that you do, is there anywhere they can find you?
yeah, I mean, you can Google me on, find my webpage at Rutgers. It's a public webpage. Google me, Amit Lath Rutgers, and my homepage pops up. I have a pretty unusual name, even for Indians. And then, there's my emails there. If you want to look at my slides for my class, I can make those public. Like I said, the class is aimed at generic population. You don't really need to have much STEM knowledge to understand, what we're teaching. I welcome any comments.
Alrighty. Well, thank you so much again. Yeah. It was a great pleasure.
Okay. Thank you, Heidi. Good luck. Good luck with the rest of your series.
Thank you. Appreciate it.
All right. Bye-bye.
Okay. Bye bye.